Hello all, my name is Stacy Arechiga, and today my group and I will be discussing our proposed synthesis for natural trialkyl substituted benzene derivative named Benwamycin E. We specifically selected this compound based on our literature search since there was no existing synthesis or mechanism for this product. The goal of our project was to propose a synthesis and mechanism for our compound. Some of our proposed mechanisms have been covered in our prior and current organic chemistry courses at CSUB, while others were proposed according to articles from our literature search. We would like to begin by providing a brief overview of the main points that my partners and I will discuss throughout this video. First, we will explain the origins of our selected compound. Secondly, we will address the importance of deriving trialkyl substituted benzenes. Thirdly, we will show and describe each step of our proposed synthesis. Fourthly, we will go through the mechanisms of our synthesis. And lastly, we will provide an estimated cost for materials needed to synthesize this compound and wrap it up with the conclusion of our video. The trialkyl substituted benzene, Benwamycin E, was isolated and elucidated from genus Streptomyces found in China in the year of 2015. This molecule was isolated as a colorless oil and determined to have a molecular formula of 17 carbons, 22 hydrogens, and 4 oxygens with multiple double bonds. High-resolution electron spray ionization mass spectrometry, commonly abbreviated as HRE SIMS, was the technique used to determine the accurate mass of the target compound. According to data from Yang's article, genus Streptomyces is important because in the years of 1940 to 2010, 40% of bioactive microbial metabolites were isolated from it. This is significant because microbial products have made significant contributions to drug development. The diverse structures of microbial secondary metabolites include almost all functional groups in organic chemistry and present a challenge for chemical synthesis. The synthesis of these molecules is crucial for the development of antibiotics, anti-tumor agents, cholesterol-lowering drugs, and many others. The following slide in this video displays an overview of our complete proposed synthesis. However, in the next slides, my partners and I will focus on breaking down the synthesis and introducing the reactions occurring throughout each step. Alexa will now explain the reactions occurring in the first parts of our synthesis.
Our proposed synthesis starts with the benzene ring as our starting material. The first step is known as the Gattermann-Koch formulation, which adds an aldehyde group to the benzene. Its mechanism will be explained later on in the video. The second step is the Friedel-Crafts alkylation reaction, which adds a methyl group. Since the aldehyde is a deactivating group, it adds the methyl in the meta position. The third step is known as the Perkin reaction, which converts an aromatic heterocyclic aldehyde into an alpha-beta unsaturated acid. The fourth step adds a protecting group to the alcohol. Both mechanisms for these two steps will be explained later on in the video.
In the fifth step, the alcohol in 2-chloral-1-propanol will first be protected with TBDSM chloride. This is done first, so the AlCl3 that is then added will attack the chloride instead of the alcohol. The Friedel-Crafts alkylation then occurs. In step 6, tetra-N-butylammonium fluoride, or TBAF, will be added to deprotect the alcohol.
Step 7 adds PCC to oxidize the primary alcohol into an aldehyde, and Step 8 adds aqueous phosphoric acid to deprotect the alcohol. The mechanism for this deprotecting step will be explained further on in the video. The last step reduces the aldehyde into an alcohol and adds the butanone group by reacting with butanone and hydronium. The mechanism and stereochemistry for this step will be explained in detail later on. As a reminder, the Gattermann-Koch formulation is the conversion of benzene to benzaldehyde. The first step starts off with carbon monoxide reacting with hydrochloric acid reversibly to produce an unstable acid chloride. The acid chloride then reacts with aluminum chloride, giving us an intermediate called the formalcation. The third step is an electrophilic aromatic substitution reaction where benzene is the nucleophile and the formalcation is the electrophile. The double bond from the benzene attacks the electrophilic carbon, adding the aldehyde. This forms a carbocation intermediate that is unstable. To regenerate the aromatic ring, a base is added. In this case, AlCl4 is our base. The base attacks the hydrogen, breaking the carbon-hydrogen bond and regenerating the pi bond. Step 3 from the synthesis, the Perkin reaction, starts off with an acid-base reaction. The sodium acetate, which is a weak base, attacks the hydrogen from the alpha carbon on acetic anhydride. This forms a carbocation that attacks the carbonyl carbon in benzaldehyde. The pi bond between carbon and oxygen breaks due to the high electron negativity of oxygen. A nucleophilic addition then occurs, forming the structure in step 3. An addition step occurs in step 3 where the negatively charged oxygen attacks the carbonyl carbon, moving the pi bond electrons up towards the oxygen. This gives the 6-membered cyclic ring in step 4. The negatively charged oxygen will move down electrons, forming a ketone. The carbon-oxygen bond will break and the sigma electrons will be moved to the oxygen, causing the ring to open. The alpha carbon-hydrogen bond will break, moving its electrons between the alpha and beta carbons, forming a double bond. The CH3COO- will then detach. In the last step, protonation occurs, forming a cinnamic acid, also known as an alpha-beta unsaturated acid.
The following mechanism shows how the carboxylic acid is protected by the T-butyl ester. The T-butyl ester is a good protecting group for carboxylic acids due to its relative resistance to nucleophilic attacks and easy removal by acidolysis. The carboxylic acid is converted into tert-butyl ester. For the deprotecting step, the oxygen of the carbonyl group was protected from the tert-butyl ester. A water molecule then attacks the carbonyl carbon. A proton transfer then takes place from the water molecule to the oxygen of the OR group. Deprotonation occurs along with the loss of the ROH group. And lastly, dehydration of the alcohol produces the alkene.
In this step, we see the mechanism for how the aldehyde is reduced to an alcohol. First, the oxygen is going to grab a hydrogen from the H3O+. Water will then grab the hydrogen, breaking the hydrogen-carbon bond, forming a carbon-carbon double bond, and then breaking the oxygen-carbon double bond into a single bond. In this slide, the oxygen will first be protonated by grabbing a hydrogen from the H3O+. The oxygen-hydrogen bond in the 2-butyl-2-ol will then be broken, forming an oxygen-carbon double bond. The carbon-carbon double bond in the 2-butyl-2-ol will then attack the carbonyl carbon. This will break the oxygen-carbon double bond, leaving a single bond. This is how the butanone group is added to the molecule.
Before adding the substituent in step 5, the following 4 groups were prioritized based on atomic number. The groups were ranged from number 4 being the least priority group to number 1 being the highest priority. As shown, hydrogen was the least priority and chloride the highest priority. Therefore, hydrogen is dashed, sent into the screen, and chloride is wedged, sent out of the screen. If the compound was rotated 90 degrees to the left, we can see how the numbering matches the R configuration. The next slide will explain the mechanism of this substituent adding to the partial product. In the first step, chlorine attacks to aluminum chloride and leaves as AlCl4 in the second step. This forms a planar carbocation that is no longer a stereocenter. In the third step, the R group forms a bond to the carbocation. Since the R group approaches from the right, it produces the R configuration. That is where the wedged methyl comes from.
The starting material for this synthesis is benzene. Benzene is available on Sigma Aldrich as an ACS reagent that is over 99% pure. 500 milliliters of the chemical can be purchased for $70.80. In this slide, we have included a table listing out the prices of each of the chemicals needed to perform the synthesis. The total cost to purchase all of these chemicals from Sigma Aldrich would be about $1,121.
In conclusion, throughout the course of this video, we introduced a new natural trialkyl substituted benzene derivative named Benwamycin E. We discussed the significance of the synthesis of these molecules for drug development. Also, we displayed our proposed synthesis and described our mechanisms to demonstrate how the target molecule can be synthesized in a lab setting. Thank you all for watching.